So if you have many questions, let's start.
Hocam probability flux'ın Gaussian varyant olup olmadığını ben tam anlayamadım. Dersteki notlarda invariant değil olarak sanırım çözmüşüz. Onu takip etmemizde invariant diyordu. Kafam karıştı.
You see, it is invariant, but the problem is, what do we define as the probability flux? That is what let's derive the probability flux. We didn't make the derivation. Now the question was this one. Let's just assume we have, just for simplicity, assume we have a magnetic field, and so this is our Hamiltonian. Okay. So this is the Hamiltonian, and the Schrödinger equation is just I h bar del psi by del t is equal to 1 over 2m minus I h bar gradient minus q over c a squared acting on psi plus q times phi. Now, if you remember how we derived the probability flux and the probability current, now we just took this equation, multiplied it with, or let's start with this one. This is what we define the probability density. Psi star psi. Let's look at how this changes. Our purpose is to identify J such that del rho by del T plus the divergence of J is equal to 0. Does such a J exist? If such a J exists, then we say that J is the probability flow. Rho is the probability density, and if the density is changing at a given point, this equation just tells me that it is flowing around that point. Now let's take the time derivative of this probability density. This will be time derivative of psi star multiplied by psi plus psi star multiplied by the time derivative of psi. Well, we know what the time derivative of psi is from our Schrödinger equation. This is, well, let me just write it in this form. This is twice the real part of psi star del psi by del t. Because the first term is nothing but the complex conjugate of the second term. Twice the real part of psi star, well, the derivative of psi with respect to time is given by our Schrödinger equation, which is psi, let's say 1 over I h bar times 1 over 2m minus I h bar Laplace gradient operator minus q over c a squared acting on psi plus q times psi star. Now q times phi times psi. Now if you look at the last term, real part of psi star 1 over I h bar q phi psi, which is the real part of 1 over I h bar phi times psi star psi. Psi star psi is a real number. Phi is a real number. It's the electrostatic potential. And if you if you multiply a real number by minus I, you get a purely imaginary number. So the real part of this combination is 0. So that tells me that del rho by del t is equal to twice the real part of psi star. Well, let me cancel these m's. And, sorry, yes. 2's cancel, 1 over m h bar psi star minus I h bar, the gradient, minus q over c a squared psi. Okay, you have to divide by I. Or, this is 1 over m h bar, the imaginary part of psi star, minus I h bar, the gradient, minus q over c a squared psi. because real part of a complex number divided by I is nothing but the imaginary part of that complex number. Now let us continue. Del rho by del t, this is equal to 1 over mh bar, the imaginary part of psi star. Let me open up that parenthesis. That would give me h bar squared minus h bar squared times the Laplacian, and plus 2q over c h bar times I, no, times divergence times the gradient times the A plus A times the gradient plus q squared over c squared A squared, this thing multiplying psi. Now the reason why I didn't write this as twice the divergence of A or A dot the gradient operator is that they do not commute. And keep in mind that when I'm writing the divergence of A over there, it's not really the divergence of A, but the divergence of A times psi. So that gradient operators appearing there, they act on everything on their right. Now again, if you look at the last term, q squared over c squared is a real number, a squared is a real number, psi star psi is a real number, it doesn't have any imaginary part. So that is basically 0. Plus I q over c h divergence of A times psi plus A times A dot the gradient of psi so this is what we have. Now let's proceed even further. Let's look at down one by one. The first term is what we had in the absence of any vector potential. Now imaginary part of psi star minus h bar squared Laplacian of psi is just minus h bar squared psi star Laplacian of psi minus psi Laplacian of psi star divided by 2i. My expression minus its complex conjugate divided by 2i is what gives me the imaginary part. This is equal to minus or plus h bar squared I over 2 divergence of psi star gradient of psi minus psi the gradient of psi star. Which is minus h bar squared times the divergence of the imaginary part of psi star gradient of psi. That was my first term. So if you what I did was this is nothing but 2i times the imaginary part of psi star gradient psi. So what I have now, the del rho by del t plus the divergence of h bar squared imaginary part of psi star gradient psi divided by mh bar, that factor, this is equal to, I have that these two terms 1 over mh bar imaginary part of this one. If A is 0, the right-hand side is 0, so we identify J as the h bar over m imaginary part of psi star gradient psi. So let us work with the last term we have. Now let me just rewrite it once more, del rho by del t plus the divergence of h bar over m imaginary part of psi star gradient psi. H bars cancel. This should be equal to q over mc times the real part of, well, here I have psi star a psi plus a dot psi. I just rewrote the above term. Well, there I have I times some number and I'm taking its imaginary part, but that just gives me the real part of that number. Now let's continue. Let's look at these terms. What's the real part of that expression? The real part of psi star a psi plus a dot gradient psi, this is equal to psi star divergence of a times psi minus a times the gradient of psi. Well, let me just write twice the real part. And twice the real part of a number is the number itself plus its complex conjugate. So let me just add that term plus psi a psi minus psi star minus a dot the gradient of psi star. Well, here also I'm using the fact that the vector potential would be real. Now I need to kind of simplify this and write this as the divergence of something. Let me first write it in terms of the components to see how to simplify it. So this is psi star del I ai psi minus psi star ai del I psi plus psi del I ai psi star minus psi ai del I psi star, which will be equal to del I psi star ai psi. Now let's see what this derivative contains. Well, this derivative will contain psi star times ai psi, the derivative of ai psi, that is the first term. The first term is, I already wrote it down. This will also contain, let's see, minus ai psi del I psi star, because in that derivative I also have this term, which doesn't appear in my above well, it does appear in my above expression, by the way. No, okay. Yeah, okay, let me just write it explicitly. This derivative, this difference is my first term. Then I have my second term, minus psi star ai del I psi, plus, for this term, let me write del I psi ai psi star minus ai psi star. No, sorry, I made it. Okay, this sign is plus from the beginning. You see, here I have a plus. I just carried it wrong. So that sign over there is plus. So this is plus. So these are all pluses. Well, if they are all pluses, it's now easy to see what's happening. Look at the first term and the fourth term. The first term and the fourth term, when I sum them up, is nothing but del I psi star ai psi. And the second term plus the third term is nothing but del I psi star ai psi. But this is nothing but, so let's see, we started by calculating this part, this expression. This is nothing but twice the divergence of psi star a psi. So 2's also cancel. Now let's go back to my previous expression. I had this expression. This is equal to Q over MC times the divergence of psi star A psi. Or if we combine them on the left-hand side, plus the divergence of h bar over m, imaginary part of psi star, gradient of psi, minus Q over MC, psi star A psi. So what we see is the current density in this case, the probability that current is, we should identify it with h bar over m, imaginary part of psi star gradient psi, minus q over mc a psi star psi. This is our probability current. Before, without the vector potential, we only had the first term over here. Now let's see if this is gauge invariant or not. Let me write it in a slightly different form. This is h bar over m, real part of psi star minus I, the gradient of psi, minus q over mc a psi star psi, or this is 1 over m, the real part of psi star minus I h bar gradient psi minus q over c a. If you remember, this basically corresponds to what we defined as the kinetic momentum. It's not the canonical momentum, it's the kinetic momentum in the sense that in the Heisenberg picture, pi is just m dr by dt. Now, if you remember, under a gauge transformation, you see we have this minus I h bar gradient minus q over c a psi goes to minus I h bar gradient minus q over c a prime psi prime. But this is nothing but e to power I over h bar lambda I q over h bar lambda minus I h bar gradient minus q over c a psi, where under the same gauge transformation psi goes to e to power minus I q over h bar lambda psi. This was how we had defined the gauge transformations. So let's look at the current density. Or the probability current. This will change into 1 over m, the real part of, well, psi goes to plus. Now psi star will go to psi star e to power minus I q over h bar lambda. And this whole thing derivative with the vector potential will go to e to power I q over h bar lambda minus I h bar the gradient minus q over c a psi. So these will cancel, and this is nothing but the initial j. So the probability current defined in this form is gauge invariant. Now, if we had identified this thing still as our probability current, in that case it wouldn't have been gauge invariant. So we have to add that additional term to obtain a probability current that is gauge invariant.
Fiziksel mana olarak peki, yani sabit bir potansiyel, Flux'ta değişime sebep olmasının sebebi bu.
Well, you see, something observable things should be independent of gauge. Gauge is our choice, and nature doesn't really care about it. So in that sense, does the probability density, for example, is it something observable? Now we can observe it, we can measure it. No matter which gauge we use, we should still be able to measure the same thing. It shouldn't change. Just like it's changed with time, you see, rho is something that we can indirectly at least determine. So it should be definitely gauge invariant. It is change in time, should also be gauge invariant. So it's something you measure. I mean, something you measure doesn't depend on your choice of gauge. So this should be gauge invariant, and hence, if we are to be able to identify something like the probability current, it should also be gauge invariant. Now, if you look at the definition, let's just integrate this J over all space. Now, if you integrate this over all space, what you get is basically the expectation value of the kinetic momentum over m. So that operator over there is nothing but our kinetic momentum, and we are acting the kinetic, sandwiching it between the states psi and psi star, between the same bra and the ket. Well, in the Heisenberg picture, this is nothing but 1 over m dr by m times dr by dt. Now, in a sense, the gauge invariance of this current density is related with the gauge invariance of the velocity distribution in my state. You see, the same state I can describe by many wave functions. And the distribution of my canonical momentum will be different depending on which gauge I use. But I'm basically describing the same state. So although the canonical momentum will be different, the kinetic momentum, which is nothing but the velocity distribution, will be the same. It will be independent of my gauge. Other questions? Well, it's just another technique to study a physical problem. So whenever you can write a Schrodinger equation, you can solve that Schrodinger equation by using the path integrals. Or whenever you can write a path integral, you can write a Schrodinger equation. They carry basically the same information. They are equivalent to each other. Well, you see, what we had, path integral is quite general. Whatever Hamiltonian you have, you can write a corresponding path integral. But that path integral will have this form. So you have an integral over all possible points and also momenta. Now you can kind of simplify this if you can write the Hamiltonian as p squared over 2m plus v of q. It's the kinetic term plus the position-dependent term. If you have this form, then the momentum integrations are nothing but Gaussians, which you can evaluate. And then that path integral just takes this form, I over h bar the Lagrangian. Well, we were mainly using this representation. Well, in the case of the magnetic field, although the Hamiltonian is not p squared of the form p squared over 2m plus v of q, still in terms of the momentum, it is a Gaussian integral. And hence you can integrate the momentum integration and you can still reduce it in this form, in the last line. So that last line is also correct when we have a vector potential and a scalar potential, which cannot be written in this form. Now, if you have more complicated Hamiltonians, where the kinetic term can also be dependent in a complicated way on the position, and the potential can depend on the velocities or the momentum in a more complicated way, let's say, where you cannot make this separation, this expression of the path integral, the first expression, will still be valid. So when can you use path integrals? Well, whenever you have some Schrodinger equation, you can use the path integrals. And when you have a path integral, you can write the corresponding Schrodinger equation for that. It's just some alternative technique to solving the differential equation. And for certain problems, it will be easier to use the path integral formalism. For certain other problems, it will be easier to directly solve the Schrodinger equation. But for example, if you want to study the Aharonov-Bohm effect, like we did, well, obtaining the same effect using the Schrodinger equation will be much more complicated than obtaining it through path integrals. Well, what is that expression we had? E to power a, b, e to power minus a. Right, so basically expression of this one. So let me define a function f of lambda. E to power lambda a, b, e to power minus lambda a. So basically what you are asked, what we want to calculate is f of 1. That is what we want. And we know f of 0, this is b. Now f of lambda, I can just write it as a Taylor expansion. F of 0 plus the first derivative of a at 0 times lambda plus the second derivative of f at 0 times lambda squared over 2 factorial plus etc. So let me take the first derivative of f with respect to lambda. It is e to power lambda a times a, this is the derivative of e to power lambda a, times the rest, b times e to power minus lambda a, plus, well, e to power lambda a times b, b doesn't depend on lambda, I take the derivative of e to power minus lambda a, and that gives me minus a times e to power minus lambda a. So derivative of f with respect to lambda, this will be equal to e to power lambda a, ab minus ba, times e to power minus lambda a. So if f of lambda is equal to e to power lambda a, b, e to power minus lambda a, then the derivative of f with respect to lambda is e to power lambda a times commutator of a and b, e to power minus lambda a. So what this tells me that if you have a function which is obtained by, you have some operator in the middle, you multiply by e to power lambda a on the left and e to power minus lambda a on the right. And then if you take its derivative, what this derivative does is it just replaces the operator in the middle by its commutator with a. So the second derivative of f with respect to lambda. Well, it is the derivative with respect to lambda d of df by d lambda, but it has exactly the same form. We have e to power lambda a on the left, e to power minus lambda a on the right, and commutator of a and b in the middle. Taking derivative with respect to lambda once more, we just replace the operator in the middle by the commutator. So this is equal to or if you want to take the nth derivative of f with respect to lambda, every derivative just adds one more commutator. So we have lambda a. So here we have n commutators. And in the Taylor expansion, I need these derivatives at lambda is equal to 0 to use that Taylor expansion on the first line on the page. Well, that basically gives me the Hausdorff formula. F of 1 is equal to e to power a, b, e to power minus a. This will be equal to b plus commutator of a and b times 1 over 1 factorial plus ab times 1 squared over 2 factorial plus ab times 1 to the power n over n factorial plus the rest. Here I have n commutators. So this is valid whatever your operators A and B are. Well, time evolution operator has such a form. If you want to evolve your operators in time, in Heisenberg picture, at the time t, this is defined as e to power I over h bar, h of t, your operator in the Schrödinger picture, e to power minus I over h bar, h of t. Well, it has exactly the same form as in the Baker-Hausdorff formula. So I can use it. Of course, there are infinitely many terms that I have to evaluate. Unless I see some kind of a pattern there, it won't be too much useful. But I can still use it. It is still correct. So is this the many questions you have? Whenever you organize some problem-solving hour. Or today. Sure. At what time tomorrow? Okay, let me check my schedule for tomorrow. I should be free tomorrow. But just to make sure that I am free, then I will let you know. Shall we pick some random questions? What is your favorite number from 1 to 40? 11. Okay, great. Don't forget the questions. 11. So page 151 in my book. Question 11. It says that using the one-dimensional simple harmonic oscillator as an example, illustrate the difference between the Heisenberg picture and the Schrödinger picture. Discuss in particular how A, the dynamic variables x and p, and B, the most general state vector, evolve with time in each of the pictures. So let's look at x and p. So what is the time dependence of x in the Schrödinger picture? What is the time dependence?
4.
Yeah, I mean just some expression which would allow me to determine the time dependence of x in the Schrödinger picture. These are the operators, the position operator. Well, okay, is it time in the, he says no. So, so this is the Schrödinger picture. If you don't see any t in your operator, it's time independent. Similarly, p. There is no t appearing over there, so it's time independent. Now let's start with any cat. Will it be time dependent or time independent? It will be time dependent. Let's say at t equal to 0, it is written as a n from 0 to infinity. And these kets n are just my energy eigenkets, which I will just, if they have the energy eigenvalue h bar omega n plus 1 over 2. So psi at the time t, this will be equal to e to power minus I over h bar ht acting on psi at t equal to 0. This will be e to power minus I over h bar h of t n from 0 to infinity a n n and from 0 to infinity a n e to power minus I over h bar en of tn. And this is how my state will evolve in time in Schrödinger picture. Now let's look at the Heisenberg picture. Well, will the position operator be time dependent or time independent? It will depend on time, and it will be actually defined as e to power I over h bar h of t x at t equal to 0, e to power minus I over h bar h of t. And x at t equal to 0 is what we call x in the Schrödinger picture. And similarly, p of t will be equal to e to power I over h bar h of t, p of t equal to 0, e to power minus I over h bar h of t. Now let's calculate some of the commutators. I will be using the Baker-Hausdorff formula. Well, this expression that we had just derived. But to use that expression, I need the commutators of h and x and p. Well, the commutator of h with x, and since we are looking at the harmonic oscillator, the Hamiltonian is p squared over 2m plus 1 over 2m omega squared x squared, the commutator with x. Well, the second term, the x squared term, commutes with x. So this will be equal to p squared over 2m, commutator with x, and this is nothing but p over m. If you just write out the commutator. I h bar p over m. Now, if you do the same thing with the commutator with p, you will get the commutator of p squared over 2m plus 1 over 2m omega squared x squared p. The first term, the p squared over 2m, commutes with p. So we are left with 1 over 2m omega squared x squared p commutator. And this is equal to plus or minus. Well, you can just think of it like this. If you just divide this by IH bar, it should be the time derivative. The force should be in the minus x direction. Now let's look at x of t. Or hold on, we have the h of p. Now, x of t will be, if we use the Baker-Hausdorff formula, and from 0 to infinity, h of x, 1 over n factorial. There are n commutators here. Now let's see, if I start with x, I take its commutator once with the Hamiltonian, I get p, up to the coefficient. If I take its commutator 2 times, well, that will be the commutator of h with p, and the commutator of h with p is again x. So all the even commutators of h, even number of commutators of h and x will be proportional to x. The odd commutators will be proportional to p. Are you following? Let me write down explicitly. H commutator with x, we said that this is I h bar p over m. X, this is 0 commutators. This is 1 commutator. Hx will be equal to h I h bar p over m. This is I h bar times minus I h bar m omega squared x. This is 2 commutators. Well, if I have hx, this will be equal to h times h bar squared m omega squared x This is m h bar omega squared. H with commutator x is I h bar p over m. So this is 3 commutators. You see, 0 commutator, I start with x. If I take its commutator with h, I obtain p. If I take one more additional commutator, I obtain x. One additional commutator, I obtain p. And as I take more and more commutators, it just alternates between x and p. So let me just, in this expression, let me divide the odd terms and the even terms. So this will be n equals 0 to infinity, n even, one over n factorial plus n from 0 to infinity, or let me say 1 to infinity, but only the odd ends. Times 1 over n factorial. Even ends, well, let's see. If n is 0, I have x. If n is 2, I have x. If n is 4, I will still have x. So all of them are proportional to x. Now, if n is 0, the coefficient of x is 1. If n is 2, the coefficient of x is m times h bar omega squared. To the power n over 2. And then I have lambda. Lambda is not 1 this time. So it is I over h bar t to the power n. Again, keep in mind, in this first term, I only have the n even terms. So there I have I over h bar t to some even number. Plus sum over all odd terms is the first commutator is I h bar p over m. The third commutator is again proportional to I h bar p over m. The fifth commutator will still be proportional to I h bar p over m. Now, if I increase the number of commutators by 2, well, that is, if I go from 1 to 3, let's say I acquire m h bar omega squared. This one. Well, basically this term over there. So I get the, now this time, if n is 1, again, it should be somehow something like n over 2. If n is 1, I shouldn't have that term, n minus 1 over 2. Now, what happened over there, you see, n is an even number, odd number, sorry. N minus 1 is an even number. N minus 1 over 2 is an integer. So that power is an integer. If n is 1, that is 0. If n is 3, that is 3 commutators. That number is just 1, so I have 1 factor of m times h bar omega squared. And then I also have I over h bar t to the power n. Okay, I need to just simplify it slightly more. You see, if I'm considering all even integers, I can write them as n is equal to 2m. M goes from 0 to infinity, and n is equal to 2m. Now, as m goes from 0, 1, 2, 3, 4, 5, that n, which I defined as twice m, it just goes over all even numbers, including 0. So that is my first sum. So that, let me not use m, let me use the k. Because m, I used it for the mass. So that's why I'm just changing its name. So let's see, this is x times m times h bar omega squared to the power k times I over h bar t squared. So let me write a minus t squared over h bar squared to the power k. And then I have 1 over n factorials. 1 over 2m factorial, 2k. That's my first term, first sum. Now in the second sum, I will do a similar thing. I will sum over k from 0 to infinity, but this time n will be 2k plus 1. So as k goes from 0 to infinity, 2k plus 1 just goes over all odd integers. So that sum becomes I h bar p over m times h bar omega squared to the power k, I over minus t squared over h bar squared to the power k times I over h bar t to the power 1. You see, I have that I over h bar t to the power n. N is just 2k plus 1. The 2 is minus t squared over h bar squared also to the power k. And that 1 is I over h bar t. And then 1 over n factorial. Hmm?
The last factorial should be
2k plus 1. This one. Now you say this one is actually 2i over h bar t to the power 2k plus 1. This one. So that one is this one. And that 2k, I'm just taking the square of this thing, taking it the square to the kth power. Where? No, that one is this one. Now let me reorganize it a bit. Sum from k is equal to 0, x times sum from k is equal to 0 to infinity of 1 over 2k factorial of minus 1, now let me have minus 1 to the k m omega squared t squared. So I made a mistake over here. You see, here I have P over M, the commutator of H with P. This 1 over M I had forgotten. So these just cancel each other. So there are no M factors left. So there is no M over here, no M over here. So this is omega t to the power 2k. Plus, let's say the last term contains a factor of p over m. That's common to all the terms, this p over m. Sum over k from 0 to infinity. I have minus 1 to the power k. It is this one over here. Well, this h bar to the power 2k cancels this one. I am left with omega t to the power k. And what else remains? I have an I over here. This h bar cancels this I. I get a minus sign, minus p over m. Then there is a factor t over here. Let me divide by omega, multiply by omega. Divided by 2k plus 1 factorial. So this becomes omega t to the power 2k plus 1. This is equal to x times x of t is equal to x times, well, if you would write it explicitly, the first sum, k is equal to 0 term is 1 minus omega t squared over 2 factorial plus omega t to the 4 divided by 4 factorial minus etc. minus p over m omega times k is equal to 0 term is omega t minus omega t cubed over 3 factorial plus omega t to the 5th divided by 5 factorial minus etc. So x of t is equal to x. This is at t equal to 0. That expansion is nothing but cosine omega t minus p over m omega sine of omega t. There is a sign mistake. That minus sign should be plus. But besides that sign mistake, well, this should be plus. But this is also what we had obtained using the annihilation creation operators, or obtain writing the differential time, calculating first the time derivatives and integrating them. This is the expression we had obtained also in those cases. And so you have basically various methods of obtaining exactly the same expression. And if you want, either you can do the same thing for the momentum, starting from the definition, or you can also look at this expression. Well, this basically tells you that P of t is nothing but m over I h bar, the commutator of h with x. So you already know what x is. Just put it here, calculate the commutator with h, and that would give you P. What about the ket? We said that this ket at t equal to 0, it had this expansion. What about at a later time? Keep in mind we are in the Heisenberg picture. The state doesn't change. Well, you see, it depends on what you call them. Psi. First of all, do they change? Yes or no?
Yes.
So these do not change. You say h of t is equal to h at t equal to 0. Since we are working with the energy eigenkets, they do not change with time. But you are right. If we were working with a general operator, not the Hamiltonian, or if we were working with an operator that doesn't commute with the Hamiltonian, its eigenkets will be different at each time. Because my operator at every time will be a different operator, and hence the eigenkets will be different. So both the n kets will be time dependent, and also those ANs will be time dependent in such a way that their product will be time independent. So the basis kets, my state ket will still be time independent. Do you want a break, or, I mean, if we give a break here, we won't have enough time to solve another question. So we have half an hour left. So let's solve one more question and then we can go. Another number? Somebody else? What's your favorite lucky number? 60. Well, that's too big. Let's take modulo 40. So that is question 20. In this chapter, at least, we have 40 questions. 60 or 16? 16. Okay. So that's fine. So we have looked at this correlation function, kind of. So this is what we define. In the Heisenberg picture, we have the position operator at t equal to 0 and the position operator at some other time t. We multiply them, take its expectation value. And we are asked to calculate this explicitly for the ground state of the harmonic oscillator. So how do these this thing changes. Now, the easiest will be to use the annihilation and creation operators. And the Hamiltonian, we had defined it as p squared over 2m plus 1 over 2m omega squared x squared. And we had defined the, let me check the explicit expression, the annihilation operator is square root of m omega over 2 h bar x plus I p over m omega, and a dagger was m omega over 2 h bar x minus I p over m omega. And the interesting things about this were the Hamiltonian was h bar omega, a dagger a plus h bar omega over 2. The position operator we could write as square root of 2 h bar over m omega times a plus a dagger over 2. Their time dependence were kind of easy. You see, Hamiltonian commuting with h, we calculate this commutator, and this was nothing but minus h bar omega a. So if we have h, 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 a, and commutators, this is nothing but minus h bar omega to the power n times a, because every commutator just brings a factor of minus h bar omega. So if we are to calculate a of t, which was e to power I over h bar h of t, a e to power minus I over h bar h of t, this will be equal to sum from n from 0 to infinity I over h bar h t to the power, I over h bar t to the power n, 1 over n factorial, and n commutators, but those commutators is minus h bar omega to the power n, a. But h bars will cancel. This is equal to e to power minus I omega t times a. Well, since I know the time dependence of a and also a dagger, just take the dagger of this one, x of t is equal to square root of 2h bar over m omega times 1 over 2 e to power minus I omega t a plus e to power I omega t a dagger. This is my x of t in terms of a and a dagger. Now let's look at my correlation function. For the ground state, this is defined as, well, the ground state times x of t, x of 0, ground state. This is equal to, if I write x of t and x of 0 in terms of a and a dagger, I would obtain 2h bar over m omega times 1 over 4 vacuum e to power minus I omega t a plus e to power I omega t a dagger, a plus a dagger, acting on vacuum. Now, a acting on vacuum on the ground state, this is 0. A dagger multiplying the ground state bra, that will also be 0, because that is basically a acting on the ground state dagger, which is 0. So this term is 0, because it is multiplying the ground state, ground ket. This is also 0, because it is multiplying the ground state bra. So for the ground state, this is equal to h bar over 2m omega vacuum e to power minus I omega t a dagger vacuum This is equal to h power over 2m omega, e to power minus I omega t, a dagger acting on the vacuum, magnitude squared, h power over 2m omega, e to power minus I omega t. That acting on the ground state just gives me a dagger acting on the ground state gives me square root of 1 multiplied with the first excited state. But the first excited state is normalized, so its magnitude is 1. So C of t is equal to h power over 2m omega, e to power minus I omega t. So if you need to calculate, I don't know, matrix elements of, let's say, products of position operator, products of position and momentum operator, etc., the easiest would be just to use the annihilation and creation operators, at least in the for the harmonic oscillator eigenstates. You don't need to do any integrations or any integrations or any derivations, etc. Well, you see, if this were not the ground state, you should have been a bit more. Let's do it for the first excited state also. I mean, it won't be too much additional work. For the nth excited state, let's say Cn of t. So let's see, when I open up that parentheses, I will have 4 terms. One term will contain 2 A operators, but the A operators lowers n by 1. So when you have 2 A operators acting on the ket n, you obtain a ket that is proportional to n minus 2. And its overlap with the ket n will be 0. And similarly, if you take the term, a second term contains 2 A dagger operators. And if you multiply the n ket n by 2 A dagger operators, you obtain a ket that is proportional to the ket n plus 2. Its overlap with the n ket is again 0. So the non-zero terms will be these ones. H power over twice m omega and e to power minus I omega t a dagger plus e to power I omega t a dagger a. Well, let's see. A dagger a acting on n is a dagger times square root of n acting on n minus 1. This is square root of n, a dagger acting on the ket n minus 1. But that is also square root of n times n. So a dagger a acting on the ket n is nothing but n times the ket n. A dagger acting on n will be a multiplied with square root of n plus 1 times n plus 1. This is square root of n plus 1 times a acting on square root of n plus 1, which is square root of n plus, this is the ket n plus 1, with the multiplied with n plus 1 times the ket n. So a dagger acting on the ket n is just n plus 1 times n. So let's go back. This is my Cn of t. This is equal to h bar over 2m omega e to power minus I omega t times n plus 1 plus e to the power I omega t times n. Or if you like, this is equal to h power over 2m omega e to the power minus I omega t plus n times h bar over m omega cosine omega t.
Hocam exact state'lerde A times A dagger'ı number operatörü olarak bu yüzden mi yazıyoruz?
A dagger times n is the number operator. So here, this is exactly the reason why we write the A dagger A as the number operator. You see, these excited states, they just contain additional packages of energy. And most of the time, we just identify them as particles. And in the solid state physics, for example, these particles, we call them phonons. So they are nothing but the oscillations of the atoms in the crystal. And so this A dagger A basically counts how many packages we have, energy packages, or in a different words, A dagger A tells us how many phonons we have in our system. So it's the number of phonons. This is the reason why we call them the number of phonons. For example, you can consider the case of the harmonic oscillators interacting with an electromagnetic field. Well, we know how to add the electromagnetic field, just modify the momentum. And if you write your Hamiltonian will have the harmonic oscillator part. Well, this will be the simple harmonic oscillator plus, well, if you just open up this parenthesis, there is an A squared term, which, let's just ignore it, it's just a time-dependent vector potential. And then you have the term A dot P with certain coefficients. Well, P is you can write it in terms of your annihilation and creation operators if you like. And so here you see the interaction of phonons with the electromagnetic field. So if there's an electromagnetic field, as your system evolves, there will be phonons created in your system, or phonons will be annihilated in your system. Because in this Hamiltonian, the n kets will no longer be our energy eigenkets because of that additional term. So they will change with time, and their time evolution will cause, basically what you will see is if you have start the ket at t equal to 0 as an n, in the n state, at t, let's say t is equal to epsilon, this is basically n plus or minus I over h bar h epsilon multiplied with n minus I over h bar epsilon. Well, your Hamiltonian now contains an h bar omega term, This is due to this part. Well, the other part will just cause your state to acquire an n plus 1 minus n minus 1 with certain coefficients. Plus additional terms. So you see, even if you start with a definite number of phonons in your system, if there is some kind of a time-dependent vector potential in your system, you see the number of phonons in your system changes with time. This is only a very small amount of time later. There is a finite amplitude that your state contains one more number of phonons or one less number of phonons. So you are basically creating phonons in your system using this electromagnetic field. Okay, so let's finish for today.